Hi, our last Teensy review concentrated more on version 3.5. In this review, we'll be taking a look at the version 3.6 and the changes that have happened to Teensy Duino.
Dali, Ack,
Synac,
Ack, Abist, ATP, CAP, CDMA, PAL, PCB, COTS, BLVDS, BGA, BNC, CEP, VUV, BSD, CELP, WACE, XDIM, CMIP, ComSat, CVBS, UART worm.
Are you sad?
Oh, what? ICIF, Fit, Do, DOS, Pan, Pick, Roast, Toe. Next Arcs, MEMS, ICW, No Odd Nan, UID,
APL,
NA,
Zigbee,
Zip.
RST. I didn't show you in the Teensy 3.5 review how my Kickstarter arrived. The package all came well padded and professionally packed. If you were a Kickstarter backer, make sure you let Kickstarter know that you did actually get your reward. If you saw my previous review video, then you will know the differences between the 3.5 and 3.6. The pinout cards only really show a small difference. There were a few mistakes in the Kickstarter cards, but you can download the updated version from pgrc.com. The Teensy 3.6 is the big brother to the 3.5. Both of them have an FPU, DSP support, onboard RTC, SD, I2S, DAX, and a really cool flex bus, allowing you to add external memory if you need it. The 3.6 has more CAN, SPI, I2C buses than the 3.5, and also has a touch sensor interface. It has everything except the kitchen sink. Oh, I see it does. Soldering time. So many pins. While I'm busy soldering up the headers, I need to point out an issue with my previous video. Do you remember this bit? A BGA is a way of soldering a component with many pins to a PCB efficiently. It is different to SMD components in that all the pins are located underneath the package. Well, what I meant to say is that the BGA package is different to QFP components. The QFP and BGA package types are both considered SMD components. It's just that the QFP component has the pins sticking out sideways and the BGA has them underneath. The QFP component can come in several styles, either low profile or thin. The previous Teensies used the QFP package. It was still an SMD, but hey, my main point was the change in package type, which might introduce some problems, such as mechanical leverage due to the narrow and long PCB, the lack of adhesive underneath the BGA. Adhesive will both secure the BGA to the PCB more and avoid short circuits underneath the BGA caused by water and other things like intermetallic growth and whiskering. If you want more information, just Google these or check the description below or on my website. Oh, look, I've finished just in time. A new version of Teensy Duino 1.31 beta has just been released, which fixes a lot of the issues I had in the Teensy 3.5 review. I didn't have the hardware to test I2S audio, MIDI and CAN interfaces, but we'll do that in a review update. Pick up the latest 1.31 beta from the pgrc.com forum site. I also installed a fresh version of the Arduino IDE 1.6.12 for my tests. Do I need to go through the installation process? Probably not. Just check out the Teensy 3.5 review. It's the same process. The Teensy 3.6 has capacitive touch capabilities. Let's check that out. Yep, my simple program worked without issue. Next. What about CPU performance? My whetstone and drystone test came up with a respectable 171 whetstones and 224 drystones. For whetstones, the 3.6 is 1.8 times faster than the 3.5 and 34 times the 3.0. For drystones, the 3.6 is 2.1 times faster than the 3.5 and 4.8 times faster than the 3.0. Once again, this is to be expected as the new Teensies have an FPU on board. Incidentally, under a continuous CPU load test, it was drawing about 85 milliamps. But hang on, you say, the 3.6 can be overclocked. Okay then, let's push it up to 240 MHz. Okay, the test seems to be finishing too quickly. Doubling the number of runs, we get a revised calculation of For whetstones, the 3.6 is 2.4 times faster than the 3.5 and 44.6 times faster than the 3.0. For dry stones, the 3.6 is 2.8 times faster than the 3.5 and 6.3 times faster than the 3.0. Holy Toledo, Batman. Who's up for making a cluster of teensies? Under a continuous CPU test at this frequency, I saw the current draw rise to a little over 100 milliamps. As a baseline, I just ran one of the simplest programs on the planet and saw a current draw of around 69 milliamps. So, what can we do with all this CPU grunt? Let's revisit the 6DOF IMU and crank up the polling rate. I'm still using the rather excellent RT IMU lib library. Note that this library does proper fusion of sensors and doesn't just pull data from the IMU. Okay, the base code works well as is, so I started fiddling around with the refresh rates and managed to hit a magical 300 Hz refresh rate. The printouts to serial that you can see are happening every 100 milliseconds to avoid tying up the CPU. This is right on the limit as it sometimes hangs the I2C bus and I have to reset. One of the issues I had with the first Teensy Duino beta was SD support, so let's give this a blast with one of the simple examples. Oh, one thing I didn't mention in my previous review was that sometimes the Teensy Helper application doesn't start up straight away and you get this sort of error. Don't panic, either click on upload again, as it may have started already, or just start it manually. Of course, if you get this error, it just means you haven't read the documentation, right? Change the chip select to the conveniently provided macro, and Bob's your uncle. Look, it works. Next on to audio testing, along with the SD card, as I had issues last time with this. I wrote a simple program that played a WAV file from SD card, which played straight through the onboard DAC and also appears as a USB audio device. Nice. Playing an MP3 from SD card worked as well. Oh, I wish my dog would stop barking. Next, onto some graphics tests. I used a cheap ST7735 display unit for this and my own graphics test to compare. It came at 1.5 times faster than the 3.5 and 1.9 times faster than the 3.0. Whilst the rotation test saw it being 2.4 times faster than the 3.5 and 3.2 times faster than the 3.0. Forcing the SPI bitrate to 24 MHz saw only a small performance increase at 1.7 times the 3.5 and 2.1 times the 3.0. But the rotation test saw twice the performance. Nice. Next, I wanted to test out an ILI 9341 based LCD screen, as these screens perform a lot better. I used Paul's standard graphics test for this one. If you compare this to the 3.5, it comes up with some fairly similar results, just slightly faster. But I reckon it should be able to go faster, much faster. Frank Bosing has come up with a highly optimized ILI 9341 library, which is a drop-in replacement for the stock library. Just pick it up from GitHub and you're away. How well does it work? Wow, look at that. Good work, Frank. I saw a similar result on the Teensy 3.5. Why such a great result? Well, this library is using what's called DMA Access on the SPI bus. This means that all your code has to do is write directly to memory and that'll get transmitted over the SPI bus without any CPU overhead. Nice. But remember, we can overclock the 3.6 to 240 MHz. Running the same test again at this speed improved things out of sight. Screen fills at 182 times faster. You know what that means. Full frame video. Frank has also come up with a demo of the 3.6 playing full frame video. You probably would have seen the YouTube video, but I just had to try it out for myself. Note, for this test, you have to use the STFAT library instead of the stock SD library. This was a bit of a headache, but more on that later. This was a test running at 180 MHz. Cool. Even better was the current draw, which only peaked at 226 milliamps and saw an average of 200 milliamps. Okay, so that's pretty hot stuff. What if we wind back the clock rate a bit, say 144 MHz? Nice. Even at 72 MHz, it was running smoothly, and at 24 MHz, it was still pretty good. A little choppy, but this is a fantastic example of the capabilities of DMA. Being able to shovel around data in hardware without software intervention makes things lightning fast. If you're desperate to try it out yourself, then you'll need to hack into your Teensy audio library. Open up the editor of your choice to edit these 4 files. Don't expect it to be the same, so work on a copy. In playsdraw.h, comment out these references. Do the same in play.sdwave.h. In play.sdraw CPP, comment out this chunk of code in play, stop, and also update. Do the same thing to play.sdwave.cpp, looking for play, stop, and update. This is all using the SDFAT library. What if you try it under the standard SD library? We find things start to get a little choppy. I didn't research the reason why, but I'm guessing that the standard SD library hasn't been optimized. So that's about it for this review. I kept it short, so I'll post an update later on. What do I think of the Teensy 3.6? Well, it's a nice little powerhouse of an MCU that is capable of so much more than I tested. And I gave it the same rating as the 3.5 for pretty much the same reasons. If you enjoyed this video, then don't forget to like. And if you want to see more videos like this, then you can now support me on Patreon. Every dollar you pledge also gets a vote in what content you'd like to see. So the more you pledge, the more you have a say. Thanks to all my current Patreons for helping me help you. Thanks for watching, and see you next week.